diameter, I guess, right? So students were having some doubts about center, right? So I thought we'll we'll revisit that center concept in the next class, right? So that's how I concluded. But in the today's class, definitely I will revisit the center part about the trees, how to find the center. The first of all, the question is, uh, what exactly you guys couldn't able to understand, whether is it what is center, or how to find a center of a tree, or there was a theorem called every tree either have a center or two centers. So which part exactly, or all the three parts? How to find center of a tree? Ajay says. Kamesh says all three. Yes, sir. How to determine the center in a graph? Okay. So I'll quickly revisit. Pay attention. So this is about. We'll start with the distance and center. Before defining a center, this with this graph, intuitively B is a center, but by saying I can guess uh, based on the intuition, but we'll see how systematically we can find a center. Before defining a center, we should understand how to define a distance. So not just in graph with not just in tree, but in graph. So we took a one simple graph here, and from v1 to v2, every hop from via edge, the available edge, every hop from one vertex to the other vertex to reach v2 from v1 is considered as a distance. We saw some example like A and E are edges. AE, ACF, BCE, BF, BGH, BGIK, BGIK, and BGIJ, and so on. There are many. So, and every edge gives a unit 1. So the distance is here 2, 3, 3, 2, 3, and 4. The shortest path between V1 to V2 is the shortest distance is 2, that is AE or BF. This is about distance. And similarly for a tree also, any pair of vertex, either BD or DA, AB, BC, the distance DC. So the distance is a hop or a edge count, the number of edges present in that. Graph will be having multiple paths, but being a tree, it's a minimally connected. I keep stressing this in every class. It's a minimally connected. So there will be only one path between any pair of vertices, right? Uh, to add to this, what is minimally connected? Um, if there are say n vertices and n minus 1 edges which connects all the n vertices is minimally connected. By adding an edge to that minimally connected graph called tree, by adding any edge between two pair of vertices, will make a circuit. Will make a circuit, and tree shouldn't have any circuits. Yeah, so we now understand about distance, right? And metrics we defined, again related to distance. Now, there's a theorem called every tree has either one or two centers. So to prove this, uh, taken an example called a graph. It's a tree also because there are no circuits, named as T. And for every vertex, I've given the farthest distance value. Okay, this is say from this vertex to this vertex, the distance is 1, but from this vertex to the farthest pendant vertex, the distance is 6. Similarly, I have updated for all the vertex. So to find a center, okay, to find a center, now this is a tree. We need to remove all the pendant vertices. The first step is remove the all the pendant vertices. If there is a tree of more than one vertex, definitely there will be a one pendant vertex, and we have seen that initially, right? Properties of trees. So in this case also there are so many pendant vertex. So pictorial representation, I will just glance. So from T to T dash, what the T dash new tree is, we removed all the pendant vertices. So this got removed, and all these four got removed, these two got removed, and this one got removed. So ultimately again, we can see that the T dash, the farthest distance, also reduced by 1. So if earlier this vertex farthest distance to reach the farthest pendant vertex was 5, now it got become 4. Similarly the others also reduced by 1. Okay, so from T dash again I will repeat the same step by deliberately removing a pendant vertices, right? So after that, I got T double dash. It's a tree. T dash is a subgraph of T. T double dash is a subgraph of T dash as well as subgraph of T double dash. So I'm just reiterating the subgraph concept. So T double dash has three vertices in fact, and if we see that the farthest distance also reduced by 1 comparatively when we compare the exact mapping of that vertex with T dash, that the parent one. So it got reduced because we removed the pendant vertices, all the pendant vertices. So this got removed, and this got removed. Only this subpart remained. Now, now from T double dash again, if I apply of the concept of removing pendant vertices, there are two pendant vertices. If I remove, I will get, in this case, I will get a vertex. That is the center vertex. Okay, that is the center vertex. In this case, I am getting only one vertex, that is the center. But there are cases that I might get an edge rather than a vertex. So in that case, that edge, both the vertex are acts like a center. That's the theorem is all about. Every tree has either one or two centers, not more than that. Means there is no three centers. If three centers, definitely I can remove pendant vertices and make one center. Right? In this example, if we remove the pendant vertex, we'll get this. This is an edge, and there are two centers for this. I mean, for this tree, we got two centers. This one and this one. The concept is clear? Yeah. So ultimately, we are just removing the pendant vertices until unless we find a vertex, it is one center or an edge. That is two center. Okay, great. So, and to connect this, we also discussed about radius and diameter. Radius is the distance, distance from the center of the tree to the farthest vertex is the radius. In a tree which has a one center is pretty easy to find. In this case, C is the center. The radius will be 3. So that's the farthest vertex or farthest pendant vertex distance is 3. So, but in this case, the farthest pendant vertex is 2. So the radius is 2 in this case. Okay, and the diameter is the highest length, the maximum length or maximum distance starting from this any pendant vertex to the other pendant vertex is a diameter. So in this case it is 6, and in this case it is 3 from here to this vertex. The distance is 1, 2, and 3, 3 edges or 3 hops, 1, 2, and 3 from here, 3 edges. So that's the diameter, and there is a note says that a radius of a tree is not necessarily half of its diameter. This is the case when there are two centers. When it is a one center, it is half of it. I mean, radius is half of the diameter. Okay. And also we saw sociological application with the same example, how why the leader has chosen the center vertex as considered as a leader in this 14-member group, because he can he's very closely connected to all other members, and he can reach out pretty easily than the others. That was the main point, just to mimic the one of the real world example. Need not be like they are connected like this in general. This is one of the case. Okay, so let's move to the final topic of unit 1, rooted and binary trees. So rooted is the name where for a given tree one of the vertex is considered as root, and in this case I have shown in a small triangle that is the root, and it's a tree of course, and it has a root. So in general when we say tree, it is non-rooted trees or free trees, and there is something called rooted tree also, means the starting point, that's the root. Okay, that's all about. So I have shown 4 figures here, rooted trees with 4 vertices. It can be like this. That 4 vertex tree can be like this, as well as like this. So yeah, I mean it is bit self-explanatory in this case. We'll move to the binary trees. Okay, binary trees are a special case, and students, please concentrate here. The binary trees which you have gone through, slightly might get a confusion, or probably you might get carried away saying that I already know. So, okay, coming to binary trees, of course, a root must have at max 2 children. That is what we know, but we'll try to define more specifically with respect to graph theory. So it's a special case of rooted trees called binary rooted trees. Okay, and it is defined as a tree in which, this is the definition, it is a tree, a binary tree in which there is exactly one vertex of degree 2. There is one vertex of degree 2, and the rest of the remaining vertices will have a degree either 1 or 3. Okay, so considering this example, the root vertex have degree 2, and rest all of the vertex, the degree is either 1 or 3. Not more than 3, not less than 1, or not equal to 2. The intermediate vertices with including leaf vertices. Only the root vertex has degree 2. Okay, so now this is not a binary tree. You know why? But this is not. Yeah, because there is one more vertex. Correct. Two vertices with the degree 2. One is the root. There is one more vertex having a degree 2. This is not a binary tree or binary rooted tree because we have mentioned that root. Okay, please keep this in mind. But in our the data structure can be considered because at max it has to have a child 2. One of course we can have, but in this case it's not. So hope the concept of binary rooted trees is clear. Yes, it's bit different. Maybe this is how the things started earlier, and then based on recent times and the situation, things have got relaxed and came to at max 2 children. There's something called complete binary tree and so many variations. But yeah, with respect to binary rooted tree in graph theory, this is how it is. There is only one vertex of degree 2, exactly one vertex of degree 2, and the rest vertices will exhibit a degree or of 1 or 3 at max. Yeah, this is not the one because the circled one is having a degree 2. It's the second vertex. Okay, so and also in the figure, I mentioned the levels also: level 0, level 1, level 2, level 3, and level 4. Those are the hierarchy, we can say, or probably the levels of uh, the tree grows. Okay, and a couple of properties we can see of binary trees. The first is the number of vertices n in a binary tree is always odd. The number of vertices n in a binary tree is always odd. So the example which I showed few minutes back, which is not part of a binary tree, that has vertex E1. So the point is, if there is a root that is 1, and if that root has to have a children, definitely it has to have 2, not just 1. So 2 more added, 1 plus 2 is 3 again. So in any level, if we add, it has to be added 2 or no. So considering that root, rest all either addition of 2 or no. So definitely it's odd. The number of vertices is always odd. Also, we can say that this is because there is exactly one vertex of even degree, and the remaining n minus 1 vertices are of odd degrees. We just saw previously the definition itself. It says one vertex will be having even degree, and the rest are either 1 or 2. So in that case, yes, the number of vertices are of course odd. And the next part is we'll try to define something here called pendant vertex. So in a given tree, if I want to calculate how many pendant vertices are there, so to calculate that, we know that there is one vertex having degree 2 and set of vertices having degree 3, we assume that, and rest all vertices are degree 1, right? Because binary tree can have only a root vertex having degree 2 and the rest are either 1 or 3. So just now what I have defined is let P be the number of pendant vertices. P indicates pendant vertex, that is degree 1 in the binary tree. So then I can say n minus P minus 1 is the number of vertices of degree 3, right? So n is the number of vertices, minus P, I will remove all the vertices of degree 1. And what is that minus 1? Anyone? What is this minus 1? Yes, root vertex, absolutely correct. Root vertex. So by removing all the pendant vertex and root vertex, I will get, degree 3 vertex. So things are clear now. And also we know that in our one of the previous classes, we have figured out the number of edges in a given tree is n minus 1. Okay, so with having all this information, I try to put those information in an equation. So we can see that equation. I will come to that. The right hand side is n minus 1 edges. And left side, in the square bracket, it's all about degrees. So to make this, if I, this 1 by 2, right, this 2, if I send it to right hand side, it becomes 2 into n minus 1. What that indicates? Every edge contributes 2 degrees, right? Hope everyone agrees that every edge will contribute 2 degrees for sure. So in that case, if the right hand side, this 1 by 2 part, the denominator 2, if I send it to right hand side, the LHS is purely talking about some degrees. The square bracket, will get into that later. So LHS rightly concentrating on degree, and also the right hand side, n minus 1 the number of edges, and each edge contribute 2 degrees. So 2 into n minus 1. They also talk about degrees. So if I want to talk in terms of edges, n minus 1 edges, then all the degrees are there divided by 2. That number of edges. So hope this equation is crystal clear. Now we'll go in that square bracket one by one. So there are 3 components of there, plus and plus. Okay, they all talk about the degrees. I have assumed that P number of vertices are having degree 1. So the first part is number of vertices having degree 1. The last part is number of vertices having degree 2. So there is only 1. So I'm just mentioning 2 degree there. Okay. I could have written 1 into P. It doesn't make any sense. Just P is good enough, right? So here 2 into 1, number of vertex is only 1 and 2 degree. The just a second. Yeah, and the middle part is the number of vertices having degree 3. So that's why 3 into n minus P minus 1. We just saw how many vertices can be of degree 3. That is n minus P minus 1. If I equate this, I can find that in a given binary rooted tree, you can find a pendant vertex n plus 1 divided by 2. Okay. Yeah, the way we started is with respect to edges and degrees, but wanted to figure out the P value, because the P is the assumption which I made initially is the number of pendant vertices. Even though we started with edges, we narrowed it down, made a relation with number of pendant vertices with respect to total n vertex, how it will be at max. Okay, yeah. Great. So now we'll also touch base few of the concept. When we say binary tree, there are definitely levels, which I initially showed level 0, level 1, level 2, level 3, and level 4. Depending on the number of vertices, the levels also grow. It can grow, complete binary tree types like fill from left to right, all, child, and it can be skewed also, just grow at one side, right? So we need to define the minimum levels it can have and maximum levels it can have. So the maximum level, and so, is represented as L max. So minimum level, if it fills, regular way, we'll see with an example. It will be the ceil function. It is. Please remember, probably it's not visible clearly or not, but yeah, whatever we get is we are doing a ceil upper level. We are rounding off to upper level. 3 point something anything is like 4. So log to the base 2 because of binary, it can have at max 2, and n plus 1 minus 1, removing it starts from level 0. This is the minimum level it can have, and maximum is something which is already defined as n minus 1 by 2. We'll quickly validate that with an example. So as I said, if consider n is equal to 11, means number of vertices in a tree is 11. So this is one way of doing it. If we apply that log to the base 2, log n to the base 2 plus 1 and minus 1 with ceil function, then we'll get the exact level as 3. Minimum it will have this, means if I have n vertices, definitely it will have minimum levels. Maximum it can go up to what? So there is no rule that this should be exist here itself. This part, right, should exist here itself. It can be here also. So the level grows. So if I do with a skewed thing, considering the fact that it should be a binary rooted tree, means root node should have at only 2 degree, only root node should have degree 2, and rest are all either degree 3 and degree 1. In this fashion, it reaches to level 5. In minimum level, it is 3 and maximum is 5. So if we do that again, a calculation n minus 1 divided by 2, we'll get that level number. So these are the just a concepts which I wanted to touch base with respect to trees. In trees, we saw few things like starting from distance, center, radius, diameter, rooted trees, binary rooted trees, and their levels and their pendant vertex, how many pendant vertex at max it can have, and few of the properties like minimally connected, tree is a subgraph, right, and it should be connected. All these things we got a good clarity. By this, I summarize like what all we gone through from day one. Mainly, we started with graph, some introduction, isomorphic graph. We also saw like how are they equal or not. Mapping should be the same, right? Subgraph concept, walks, paths, circuits, and connectedness components. When there is a disconnected graph, multiple components. And we saw Euler lines, so Euler graphs, open Euler line, Hamiltonian path, and circuits. In Euler line itself, we also saw arbitrarily traceable graphs. Then we stepped into trees, properties of trees, and distance, center, radius, along with diameter, and rooted and binary trees. So by this, I can say that those who are very attentive in the class definitely will be having a good clarity with respect to visualization also, because I've tried my best to put majority of the figure wave pictures wherever it is is not clear in Unit 1. Any concept? Euler graphs are not clear, sir. Okay. Ramya says, yes, sir. Yes, sir. Probably I think everything is clear. Ajay, Euler graph. So, for you, any graph has a Euler line, definitely it's a Euler graph. Now, what is Euler line? So, it's a closed walk, first of all, and the constraint is on edges. Other than Ajay, anybody having same doubts or issues in understanding Euler graph? Should I touch base or how is it? So I want the count. Hamiltonian Euler is the confusion or just a Euler is the confusion? If no one responds, I take that. For Ajay, it is okay. Karthik Euler is not clear. Okay, fine. So this probably, let me go to those examples. I don't think I've started with trees here. Yeah. Maybe in this Hamiltonian. Okay. Yeah, Euler. So quickly, so the idea is it should be a closed walk, means the starting and ending vertex should be the same, and it should we should try to cover all the edges. We should try to cross all the path. So that's why Euler is the one who solved the Coensberg bridge. If we go to the first classic problem of graph theory, Coensberg bridge, graph C itself is a Coensberg bridge problem. Exactly have four banks. Four banks means C and D. I think they are the islands and A or B the banks. So four lands A, B, C, D, and there were seven bridges. Like if I consider those bridges as path to go from A to island C and island C to bank B, right? So those bridges can be considered as edges. So now the idea was wherever we start and we should come back by crossing all the edges. The constraint is on edges, not on the vertex. Vertex can be repeated. So the only thing is the starting and ending should be the same. So these are the three examples. We can't get a Euler line in this. So wherever we start, we end up in to reach to the same vertex or same circle or same point, the starting point. We have to cross an edge extra time, or twice we have to go through. So in Coensberg bridge problem, there is no Euler line. So quickly in A and B, yes, if I start with from the center, right? So I will go with the right hand side of the let's say there are two moons are there, like half circle moons. One is upward and the downward, right? So from center, I will take the right hand side of going upward moon and come back to the leftmost part of the upward moon, and again come back to the center. Now take the downward moon path, go to the rightmost point, and then again come back from the rightmost to leftmost, taking the other path, and again come back to the center. So in this is a Euler line. We started at center, we reached the center. Yes, vertices are repeated, but we covered all the edges. The only constraint is on edges. If any, this is all three are graphs. Okay, all three are graphs. Any graph has a Euler line is also a Euler graph. Very simple. So is it clear somewhat now? I mean, I have shared the materials also. We'll go through once and then probably we'll touch base, because Euler things will again pop up in the coming units, and few of the topics probably I'll just say and we'll explore more in the upcoming units. So in that case, we'll revisit if it is required. All the edges should cover only one time. That's why the Koenigsberg bridge problem is not solvable. Euler proved that it cannot be covered, right? Because there is no Euler line. Because, okay. So in this, if I say start with A, I will reach to C with one edge, and I will go to D, and then again I will come back to A. Again I will reach C with the other edge. Okay. Now I have covered the upper part of A, C, A, and D. Now I will take one of the edge from C to B in two parallel edges, and then I will go to D. See, or probably if I don't go to D, I will go to C again with the other edge. Now I have left with one of the edge. I couldn't able to traverse that. I traversed only the upper part completely and the C to B part. I couldn't travel B to D part. One edge got missed out. So if you try in any of the way, definitely one bridge or one edge we won't able to traverse. So that's why there is no Euler line. And since there is no Euler line, it's not a Euler graph. Euler graph is starting point should be the same. If it is not, then it is an open Euler line. If you are able to cover all the edges, but the starting and the ending vertex, or starting point and the ending point, or the starting place and the destination where we reach by covering all the edges, if they are not the same, then it is open Euler line. Okay, since Euler line talks about the closed walk, has to be the same. Starting and ending vertex has to be the same. If it is not same, then concept comes of open Euler line. But the point is, cover all the edges only once. Only once. Hamiltonian, exactly the same closed walk. Hamiltonian circuit I'm talking about, not the path. Circuit, starting and ending should be the same. It's a closed walk. All the vertices should be covered only once, or all the vertices should be traversed only once. Euler line is about the edges. There it is about the vertices. So probably if you look my the materials, and if you open the textbook, it is almost the same. Just in a colorful way I presented with, and hopefully the concepts are very clear. So you can refer the textbook also in probably the same information you will get what's in the material. And yeah, so successfully we completed the unit 1, and we'll move to the unit 2. By the end of the week, probably I will keep sharing the materials. Okay, and I expect the same with respect to the attendance from CR also. So keep updating all the attendance. You can see 48 students are present. So 48 minus 1. I don't know whether it considers me also in this participant list. 47. So 47 students are present. Keep updating regularly, and at the end of the week, probably I will go through. Thank you. So we'll close about the trees and graphs, and we'll step into the more specific topic about trees. So is the spanning trees. Spanning trees is a topic probably. And a quick question here, like in your data structures, did you guys solve anything related to Kruskal's algorithm or Prim's algorithm? Yeah. So now spanning tree, you guys didn't solve. Minimum spanning tree. Yeah. That's the one. Minimum spanning tree is the word. So it's almost the same. Concepts wise, uh, we'll touch the all the possible concepts and we'll see whether it's the same or not. So a given graph has numerous subgraphs. So if it has n vertex based on the edges, whether that edge is present or not. If it is present, it's part of the graph. It is not present, it is part of other sub. It's other graph, that is subgraph. So how many combinations we can get? 2 to the power of e. So just either it is present or not, present or not. In that way, we can get 2 to the power of e distinct combination of subgraphs based on the edges. Okay. So for any given graph, there are so many subgraphs, but all subgraphs are not trees. That's the whole point here. So only some of these subgraphs will be a trees. I mean, yeah, of course. There can be a subgraph which has a circuit also. So all subgraphs are not a tree, and all trees which are these, right? Like I have a bigger graph bigger graph G, and say some 100 subgraph can be made. In these 100 subgraphs, not all 100 subgraphs are tree. Can be some 25 to 30, which doesn't have any circuits. So those 20, let's say 30 subgraphs are tree. But are these 30 subgraphs which are tree a spanning tree? No. That's also not point. That's the whole point. So what is spanning trees? So a tree, T is said to be spanning tree of a connected graph G if T is a subgraph of G and T contains all the vertices of G. There can be a subgraph with n minus x vertices and it's a tree. But that is not a spanning tree. If a graph has n vertices, the spanning tree, any tree which has n vertices with minimally connected, that's why I call it as a tree. It has the same number of n vertices, then only it is called as a spanning tree, right? Concept clear with respect to graph, graph, subgraph, tree, and spanning tree. Graph is a superset. Yeah, subgraphs are next level. Trees are the grandchild level. If graph is a parent level, child is subgraph, and in that hierarchy, tree comes at the third level, and then comes the spanning tree. So it's a very specific kind of a tree or specific kind of a graph, I can say. So let's quickly take the example which I've taken the same thing to explain about the distance and all, the same graph. So if I want to Find out a spanning tree. Yeah, the green one covering all the vertex and doesn't have any circuit. First of all, it is a tree and it is a spanning tree. Difference is the tree and spanning tree. Spanning tree should cover all the vertices. Tree, it is just circuitless. Graph is tree. So this is a spanning tree. So quick question is this the only one solution for two? I mean, is this the only one spanning tree for this given graph? Definitely not. So there are two spanning trees here. So the one which takes, I will just mention the edge A, E, J, I, G. This is one spanning tree, and the other one is J, E, F, H, and B. These edges cover all the vertices. There can be multiple spanning tree. Okay, just to get a clear idea, and yeah, there is something called in this figure, right? The highlighted one is a spanning tree, and the rest are edges are named in C1, C2, C3, C4, right? And the highlighted path they are named as B1, B2, B3, B4. In when the concept of tree comes, especially spanning tree comes, the the edges which participate in a spanning tree they are called branches. Okay, branches. And the rest of the edges which are part of graph but not part of spanning tree they are called chords. Those are the keywords we'll follow in the graph theory. We'll see more. So that's why the naming convention for branches it's B1, B2 and chords C1, C2. Okay, and yeah, what I will do is will because there is a connected concept. We'll stop here for this today's class. We'll join for the next class. Probably tomorrow is the next class. We'll resume from the same topic or same slide. Okay. Any questions? Okay, then I'll take that as no questions. See you in the next class. Thank you. Yeah.